Okay, hi guys. So welcome to part 1 of topic 17, the wave nature of light. So this topic here, probably the hardest of the waves questions some people find. I find that they often ask a lot of questions on this topic as well, just because it's a little bit more difficult. But we'll go through it, and I'll try and break it down for you as best I can. You'll find it's actually not as difficult as you might think. Okay, so light travels as a wave. Okay. The question is, of course, the meme, is light a wave or is light a particle? And the answer is yes. Okay, so light travels as a wave, therefore it has to undergo the same properties. It has to be reflected, which is easy, it is. It has to be refracted, go back to optics, we see that. You have to have interference and diffraction. Now that's something we need to show. So how did they prove that? Well, they did it with Young's slit experiment. Okay, so basically had a monochromatic. Now note the word here is monochromatic. Okay, you need to use that, right? Meaning one wavelength. Okay, because if you have multiple wavelengths, you get the rainbow effect. So what he did was he had monochromatic light source, so it hit the slit here, and you caused diffraction of diffusion. Okay, and then it hits the second one. So then you have two light sources, if you will, with the same wavelength, and they interfere with each other, and you get your interference pattern. Okay, as you can see here on this side here. All right, where you get the lights where it was constructive and the dark slides are where it was deconstructive. Okay, so that's basically how they did it. All right, you set it up as shown, slide it through. All right, okay. Now, color has different wavelengths. This is how you see the rainbow effect. Red has the largest wavelength and violet has the smallest. Okay, this is why when you see the rainbow, you'll never see it upside down. You'll never see violet on the top, red at the bottom, ever. It'll always be red top, violet at the bottom, okay? All the time, all right? Just because when it breaks, that's the way it's going to go. It's going to refract more than its counterparts, okay? The diffraction grating, this is important. How the diffraction grating works, it's a piece of transparent material with a huge number of opaque or black parallel lines in the engraving, okay? This is to keep the slit width small because light has a small wavelength, okay? And the only way to cause this the interference pattern is we need to get it the same size as the wavelength, okay? So, generally, they're going to give you lines per millimeter, which you need to convert to lines per meter, okay? And I'm going to show you how to do that. That's often the questions asked. It's very easy to do, okay? Here you go, all right? You will often be told in the question that the grating has n lines per meter, multiply by 1,000 to get the number of lines, and then invert to get d, okay? What do we mean by that? If you're still confused, we'll be going through it now soon enough, and I'll explain it all to you, okay? So, the diffraction grating, your derivation, you've all seen it. N times lambda equals d sine theta, okay? N is the number of images, lambda is the wavelength, d is the diffraction grating, theta is the angle, okay? So how do you prove this? How do you derive this formula, all right? Easy way to do it, draw this diagram here on the left, okay? With all these symbols in it, all right? What you can do then is if you look here, you've got a right angle triangle. Okay? Okay. So we can pull that triangle out. So my right angle is there. Theta is up here. My hypotenuse is D. And this is n times lambda. Okay? So, for two rays entering in direction, making an angle with the grating, if they are brought together by a converging lens, their path difference is a whole number, n times lambda. So if you bring a converging lens up here, you get an n times, so that's 2 lambda, that'll be 3 lambda, 4, 5, 6. So if you keep doing that up, okay, the lines will cross, okay, at an n times of a whole number, n times lambda, n times the wavelength, okay? So then for part 2, you can simply draw the diagram here and you say, well, for trigonometry, we can now find out what this n times lambda is, okay? We can find what this is, okay? So we'll use sine theta is the opposite over the hypotenuse. So sine theta, n times lambda over d, lambda equals d sine theta. Okay? So n times lambda, sine theta equals n times lambda over d, n times lambda equals d sine theta. There you go. That's your equation. Okay? All right, so it's very straightforward. That's your derivation. You basically just you're drawing your diagram. You just draw a diagram for this one. Draw your diagram. Draw your triangle. Pull the triangle out, and you can show it there. Okay. So, understanding the extra part wavelengths traveled by the upper wave is an integer number of the wavelengths greater. Understand the angle on the top. So all the angles, by the way, are the same. So this angle equals this angle equals this angle, all the way down. Okay, they're all the same angle. Okay. Understanding the extra part length, yeah, we've kind of covered that. All right, so the number of images found at each side of the central image. So basically what happens is your diffraction grating is here, and you have your screen over here, and your light hits this, and it spirals off like this, creating all these images, okay? The central image is always called n equals 0, and these then are n equals 1, n equals 2, all the way up, and n equals 1, n equals 2, all the way down. That does not look like a 1 or a 2. Apologies there. Okay? All the way down. Okay? The maximum value for sine theta is 1. Okay? Reason being, the maximum angle is 90 degrees. Okay? Now, why is that? Simple. You have your diffraction grating here. Okay? This is your diffraction grating. Okay? Your angle is going to go from the central image theta. Oh, that they don't look like theta either. Okay, my pen isn't as accurate as I'd like it to be. It's not really picking up what I'm trying to draw. There we go. Okay. Now, you cannot extend that angle backwards. In other words, I'm going to get a different color here just to try and go purple. Okay. You cannot have an image going backwards. Okay, the maximum distance you can go is a 90-degree angle. If you go to 91, the image would appear behind the diffraction grating, which is, of course, impossible. Okay, so that's why the maximum angle is 90. So therefore, the maximum value sine is going to be sine 90, which is 1. Okay, so to get the maximum number of values, the maximum number of image, for the max images, so max, not max, max n. For max n, theta equals 90. Okay? So theta has to equal 90. So for n max, and you have to state that in the question. They say, find a max number image. You have to say, well, for n max, theta equals 90. Therefore, n max. Therefore, n times lambda equals d. N equals d over lambda. There you go. Okay? Now, there's another trick. I think, let me see now. I'll look at the questions. Yeah, so one of the questions I'm going to do is going to refer to this, so I'll come back to this again. There's another part to this. Some of you already know it, and if you don't worry, we'll cover it now in a second. So we're going to answer a few questions here now. So, problem 1. Monochromatic light. So I'm going to answer all these questions, and that'll be the end of this video. And in the second video, we'll take up for the second part and cover us to the end. Okay? So monochromatic light falls onto a diffraction grating. It strikes the grating at right angles to the grating spacing d. The diffraction constant, the grating constant, d, is 2.8 meters. The second order image, n equals 2, is at an angle 65 degrees. Find the wavelength. Values on the left hand side. N times lambda d sine theta. We want to find lambda, make lambda the subject. Fire in every single one of your values. Now we should end up with 1.269 10 to the minus 6 meters. Okay, there you go. That's our wavelength. Problem 2. So, a diffraction grating has 500 lines per minute. Get used to this. We need to find d. Find the grating constant. The grating constant is d. So that's going to be 1 over 500. And then we got to convert millimeters to meters. 1 over 500,000. There you go. That's it. That's all you have to do. Every time. 2 by 10 to the minus 6 meters. Okay? That should be a comma. Actually, let's get rid of the comma. It looks like that's the point. I don't want to confuse you. That's all you do. Diffraction grating has 400 lines per millimeter. What's the diffraction constant? 1 over 400,000. The diffraction gradient has 8 lines per millimeter. That's too low, but we'll just say 8. What's the diffraction constant? 1 over 8,000. You always multiply by 1,000 and put it under 1. That's it. You don't even need to do the last step. Often I usually just leave it as this and fire it into the calculator to get my answer. Oftentimes you will get 3 marks for doing that conversion. They'll give you the lines per millimeter and they usually give 3 marks for the D. Okay? Problem 3. All right, so this is more like an example question. A beam of monochromatic light of wavelength, so we got a wavelength, 5 by 10 to the minus 7 meters, is indented normally on a diffraction gradient of 600 lines per millimeter. A screen is placed 0.4 meters from the grating, and they want find the distance from the second order image from the central image. We don't have theta either. Okay, so what we have here is we have our grating, we have our screen, we have our light hitting it. Our light is 0.4 meters, and we're looking for n equals 2. That's our central image, n equals 0. Right, find the distance of the second order image. So we're trying to find this distance, which we will just simply call x. I don't care what you call it. You're going to call it a, b, c for all I care. I'm just going to call it x. We want to find that distance. So what do we have here? Do we not have a right angle triangle? We do. But the problem is we don't have an angle yet. So how do I find the angle? Go to your log tables. What equation has everything bar 1? That's what you always do. Look for the equation missing to it. Do we have d? We do. Do we have lambda? We do. Do we have n? We do. Do we have theta? No, but we're looking for it. There you go. That's the equation we're going to use. So rearrange it, make theta the subject. So that's going to be n times lambda over d sine inverse. And that, firing all your values, should give you 36.86 degrees. There you go, 36.86 degrees. So now that we have that, we can now look at a right angle triangle. So I'm going to rub out. We now know what that is. That is 36.86. So now can we find that distance? Sine, cos, or tan? Be careful now. Look at it. That is our opposite. This is our adjacent. This is our hypotenuse. Now, some people do, I don't know why they do it, but they go off and they find the hypotenuse by using the square of the hypotenuse is equal to the sum of the square of the opposing two sides. All right? Fine, but it's a waste of a step. What can we use? We could simply use tan. I'm going to just change this back to being red again. Okay, so you can just simply go tan. So we're looking for x. Fire in your angle, and we should get a distance of 0.299 meters. See how I answered that question? The good news is they're pretty much all like that. They follow that pattern. We have a distance from a screen, find this order image or whatever, okay? You don't really change much, okay? So that's kind of the handy thing about these ones. They're actually not that difficult, okay? Once you get the hang of them, practice them. I have another question to do now. It's very similar. I have 2 more to do. So, a diffraction gradient has 200 lines per millimeter ruled on it. Monochromatic light source, so write out our values. So what is D? D, 1 over 200,000. Monochromatic light source of wavelength is indented normally. What is the highest order image found? Okay, so looking for n max. It's going to call it n. So at n max, you have to mention that theta equals 90. Okay, so you could either say at n max sine theta equals 1 or theta equals 90. Either way, I always go sine theta equals 1. So therefore, n max equals d over lambda, which should give me 8.06. What is the highest order diffracted image? So therefore, now, key thing here, you always round down. It's just happened that it happens to work out this way. We're used to, if it's above 5, you round up. We don't here. Okay? What this is asking is how many images do you see on the screen? What's the highest image you can see on either side? Highest order. Okay? So if it was 8.9, the answer is 8, not 9. Why? Because you don't see a ninth image. You can't see a half an image. You're only going to see an image or nothing. Okay? So it doesn't matter if this is 8.9999, you only see 8 images. The ninth image does not form. Okay? Does that make sense? So you round down. Okay? So a lot of people get caught with that. You'll see that now in the next question we do. So this is going to be a bit long. So I might have to roll this up to get the space. So an interference pattern is formed on a screen when a green light from a laser passes normally through a diffraction grating. The grating has 80 lines per millimeter. And the distance from the grating to the screen is 90 centimeters. Okay, so I'm just going to call that distance. The distance between the third order images, hold up here now, I nearly got caught there. The distance between the third order images is 23.8 centimeters. Calculate the wavelength, so we want to find the wavelength, but they didn't give us the angle, and they want to find n max. Right, so what do we have? We draw this out before I figure out what I'm going to do here. Draw your diffraction grating, draw your screen, draw the light hitting, and then we'll draw up here. And then we'll finish it off, n equals 3. Okay, now the distance from these two is 0.238 meters. So what would the distance from N0 to N3 be? It'd be 0.119. You see? 0.119. Now we're also told that our distance from the screen is 0.9. So we just need to find our angle there, don't we? So, we're a little stuck, are we? So the first question is, let's look at the question. Find lambda. Well, n times lambda equals d sine theta. We don't have. So we need to find that. So again, remember what we did in the last question. Look at what we have. We have a right angle triangle here. Okay? We have a right angle triangle. If we can, I'll delete the bottom bit just to make it a little bit easier for you to notice that. You see, if we cut that in half, we have a right angle triangle. So again, equals the adjacent over the opposite. So theta equals the tan inverse of 0.119 over 0.9. So my angle here is going to be 7.532 degrees. So now we can solve that, can't we? So now lambda sine theta over n, yes. And I worked that out to be, I ended up getting 5.5083 by 10 to the minus 7 meters. There you go. Okay. Now, that's part one. So again, didn't I tell you, it's pretty much the same thing. They just went a little bit backwards this time. The previous time you had to find the angle between them. This time they wanted, or between the nth order images, they wanted you to find this the last time. This time they asked you to find the wavelengths and gave you that. So they'll always give you enough, always draw it out. Once you draw it out, you realize it's a triangle. It's always a right angle triangle. Work it back from there every time. Very easy. So we've answered part one. That's done. Now we get on to part 2, the maximum number of images that are formed on the screen. And again, so at n max sine theta equals 1. Okay? So therefore, n equals d over lambda. So d, what did we work that out? So 1 over 80,000, and lambda is what we got literally just 2 seconds ago. So you should work out this to be n equals 22.7. So therefore, n max is 22. So there are maximum 22 images. You do not see a 23rd image. So therefore, total images on screen equals 45. Where the hell did I get that number from? What's going on there? Have I completely lost it? Possibly, but that doesn't affect the fact that this is the correct answer. Why? Your screen is here, your diffraction grating is here. Don't forget, n equals 0. So that means there is a maximum, n equals 22 on this side, n equals 22 on this side. 22 plus 22 is 44, plus n equals 0 gives us 45 images. You see? There are 22 images on either side, but don't forget we have n equals 0. That is also an image. So you have 22 plus 22, 22 on the left, 22 on the right, and the central image is 45. Always remember that. When you get n max, you get the highest number of all images. What that means here is that there are 22 images on the left-hand side, 22 images on the right-hand side, and there's also the final image, n0, n equals 0. Okay? All right. We leave it at that, guys. We'll take it in part 2 to finish it off with polarization and a few other questions. Okay? All the best. Leave any questions or comments in the